Now in this lecture, we'll make an alternative definition of the Poisson process, which will imply the first definition. First, we need to define something called independent increments. Define an increment in a counting process from time t to time t prime as the amount of change in the process from t to t prime. That is the number of arrivals from t to t prime. A counting process is said to have independent increments if for every integer k and every set of time instants from t1 to tk that follow each other, the random variables n of t1, the increment from t1 to t2, the increment from tk minus 1 to k, so on, are statistically independent. Okay. So basically, the number of arrivals in disjoint intervals are independent of each other. Now, for the Poisson process, this holds because we showed that for any time t, okay, the amount of time z1 until the next arrival after t, remember Sn plus 1, this is Sn, is independent of the value of n of tau for tau less than t. Okay? Let's, t1, t2, tk be defined like this. And this means that z1 is independent of z1 is independent of n of t1 and tilde t1 to t2 and tilde tk minus 1 to tk for t1, t2, tk minus 1, tk less than t. Okay. Similarly, subsequent interarrivals after z1 are also independent of these. Okay? Consequently, the Poisson process has the independent increment property. Now, we can use this property in an alternative definition of the Poisson process, which I'm going to call definition 2. So, definition 2 of the Poisson process is a Poisson process is a counting process n of t such that 1, n of t is Poisson distributed such that the probability that n of t equals k is given by lambda to the k e to the minus lambda over k factorial for k bigger than or equal to 0. Secondly, n of t has stationary increments, meaning the increments, the distribution of the increments depend only on the amount of time passing from t to t prime, meaning only on the difference t prime minus t and not on the actual values of t and t prime, meaning the amount of change in the process does not depend on where the interval is located, but on the length of the interval, which is something we showed in the previous lecture. And following from definition 1. Anyway, the third item in definition 2 is n of t has the independent increments property. So this is a standalone definition as an alternative to definition 1 that we introduced last time. Let me repeat. For any t, the number of arrivals, n of t, has the Poisson distribution, meaning the probability that there are k arrivals in an amount of time t is given by lambda to the lambda t to the k e to the minus lambda t over k factorial. Okay, so it is a Poisson process at rate lambda has the property that the number of arrivals in amount of time t has an average value equal to lambda t. The expected number of arrivals in time t is given by lambda t, and the distribution of the number of arrivals is Poisson distributed with mean lambda t. Lambda t to the k e to the minus lambda t over k factorial. Okay. Secondly, n of t has stationary increments and it has the independent increments property. It can easily be shown that definition 2 implies definition 1. How would you do this? Well, what is the probability that x1 is larger than t? What is the probability that the first inter-arrival time is larger than t? This is the same as saying that the probability that no arrivals happen this is the same as saying that by time t no arrivals have happened yet, because this is time 0, this is time t, and we are exploring the probability that the first inter-arrival time is more than t, meaning the first arrival will happen after time t. In other words, the number of arrivals by time t is equal to 0. Okay, so well, using the first item in definition 2, n of t is Poisson distributed, so this is computed as lambda t to the 0 e to the minus lambda t over 0 factorial, which is simply e to the minus lambda t. But this shows that the first inter-arrival time is exponentially distributed with rate lambda. Okay, so that checks the first item in definition 1. Inter-arrival times are exponentially distributed. For the second and third items, we will apply so IID. Okay, not second and third items. I'm sorry. Definition 1 was the inter-arrival times are exponential and independent. Okay, so the independence or the IID exponentialness of the inter-arrival times is ensured by 2 and 3 in the second definition, because if n of t has the independent increment property, this will follow, from this it will follow that the time until the next arrival is independent of x1, and this you should show this separately. I'm not going to devote further time on this. Instead, I want to focus on a very quick example that shows the properties of the Poisson process in action. Okay, suppose returning to the model for bus arrivals that start at time 0, okay, and go on as a Poisson process. Suppose I arrive at the bus stop at a given time t. Okay, so I arrive for example, at 7:30 a.m. Okay, and the bus arrivals have been going on as a Poisson process at rate lambda equals 1/10 buses per minute. Okay, I want to answer the following question. First of all, given that I arrive at this arbitrary time 7:30, what is the expected amount of time that I wait until the next bus? Well, I know from last lecture that the distribution of the amount of time until the next bus is exponential regardless of my time of arrival because of the fresh start property that we discussed in the previous lecture. So then the expected amount of wait until the next bus is 10 minutes. Okay, so here's another question. My friend is going to arrive at 8, okay? My friend will arrive at time 8 a.m. All right. So what is the probability that while I wait for my friend to arrive, 2 buses go by? Okay. So that is the probability that there are 2 arrivals in the Poisson process in the interval between 7:30 to 8. So in an interval of 30 minutes, what is the probability that there are exactly 2 bus arrivals? Well, that is easy because I'm going to use this property, or if you want, you can view it as part of definition 2, that bus arrivals are Poisson distributed. So the probability that there are 2 arrivals is equal to lambda t, which is 1/10 times 30. It's 3 to the 2 e to the minus 3 over 2 factorial, which is 4.5 e to the minus 3. Okay, now how about what is the probability that my friend arrives before the first bus? Okay, what is that? Well, that is the probability friend arrives before the bus. Well, that is exactly the event that I do not miss any buses waiting for my friend. It is also equal to the event that there are 0 arrivals from the time period from 7:30 to 8, right? And that is really easy to compute. That is simply e to the minus lambda times t, where t is 30 and lambda is 1/10, so e to the minus 3. So finally, I want to pose an interesting question. Given that I show up at t equals 7:30, okay, and there was definitely a bus arrival before me, and there's going to be a bus arrival after I arrive, what is the distribution of the time interval between these 2 buses? Is it an exponential at rate 1/10? Or is it something else? So here is the argument for this. From the time that I show up to the next time instant, I showed already by the memorylessness of the exponential, therefore by the memorylessness property of the Poisson process, that this residual amount of time is exponentially distributed at rate lambda. By a similar argument, going backwards in time, from time t backwards into the previous bus arrival, the amount of time is also exponentially distributed. So z then, the time interval between the 2 buses, the one before I arrive and the one after I arrive, is the sum of these 2 exponentials, which is Erlang of order 2, parameter lambda. So the expectation of the interval that I sample by arriving at a random time is 2 over lambda, which is in this example 20 minutes. So just by showing up, I sample a bus inter-arrival time which is twice as large as the mean bus inter-arrival time. Does this mean I'm unlucky? Well, this all points to what is sometimes known as a random incidence paradox, meaning when you arrive randomly, you tend to sample a large interval. Okay, because, well, when you sample a counting process at random, uniformly at random, you are more likely to sample large inter-arrival durations. All right, so later on we will have more interesting we'll see more interesting consequences of this random incidence paradox.